Welcome to my sleep science channel. Like, subscribe, and tell me where you are watching from. Tonight, we begin a calm and fascinating journey toward one of the most mysterious places known to humanity, the center of our galaxy. This is a place that no person will ever physically visit. Yet through careful observation and decades of discovery, scientists have managed to uncover remarkable details about what lies there. Our journey begins not with complicated equations or abstract theories, but with something simple and familiar: the night sky itself. For thousands of years, people have looked upward and wondered about the pale band of light stretching across the darkness. On clear nights, far from city lights, this glowing river can still be seen with the naked eye. Ancient shepherds, sailors, travelers, and storytellers all gazed upon it. They gave it names and created myths to explain its presence. Today we know that this hazy band is our home galaxy, the Milky Way, a collection of hundreds of billions of stars spread across unimaginable distances. From our position inside the Milky Way, we do not see the galaxy from the outside. Instead, we experience it from within, rather like standing inside a vast forest and trying to understand its shape by looking between the trees. The stars surrounding us are only a tiny fraction of the whole. Beyond them stretch enormous spiral arms, rivers of gas and dust, ancient star clusters, and regions so distant that their light takes tens of thousands of years to reach Earth. Our solar system occupies a quiet neighborhood located far from the galactic center. The Sun, accompanied by its family of planets, slowly circles around the center of the Milky Way at incredible speed. Even though we are moving at more than 500,000 miles per hour, one complete journey around the galaxy takes approximately 230 million years. Dinosaurs lived and disappeared during only a small portion of a single galactic orbit. Because we live so far from the center, the true heart of the Milky Way remained hidden for much of human history. Looking toward the middle of the galaxy is like trying to see through an immense cosmic fog. Vast clouds of dust block visible light, preventing ordinary telescopes from revealing what lies beyond. For generations, astronomers could only guess what secrets might be concealed there. Yet hidden behind those dark clouds exists one of the most extraordinary regions in the universe. Countless stars crowd together in a relatively small space. Strange streams of gas twist through the darkness. Powerful radiation emerges from invisible sources. Enormous forces shape matter and energy in ways rarely seen elsewhere. At the very center, occupying a region smaller than our solar system, lies something so powerful that millions of stars revolve around it. Long before modern astronomy provided answers, humanity imagined many possibilities. Some believed the center of the heavens held divine realms. Others imagined celestial fires or eternal stars. These ideas reflected the natural desire to understand what could not yet be seen. As technology improved, each generation added another piece to the puzzle. The story of the galactic center is also a story about patience. Many discoveries required decades of observations. Some astronomers spent entire careers tracking tiny movements of distant stars. Others developed instruments capable of detecting forms of light invisible to human eyes. Piece by piece, the hidden heart of the Milky Way slowly emerged from darkness. What makes this story especially remarkable is that everything we know has been learned from afar. No spacecraft has traveled there. No probe has approached its deepest regions. Every detail comes from faint signals crossing vast distances through space before finally arriving at Earth. From these whispers of light and energy, humanity has reconstructed an astonishing portrait of the unseen. As the night grows quiet and the stars continue their ancient dance above our world, it becomes comforting to remember that we are part of something unimaginably large. Our planet is only a small island orbiting one ordinary star among billions. Yet through curiosity and careful observation, we have begun to understand the great city of stars to which we belong. Deep within that cosmic city, Hidden behind curtains of dust and distance lies the destination of our journey, a mysterious place that has inspired questions for generations and continues to reveal new surprises even today. The center of the galaxy remains one of the greatest wonders in the universe, a region where ordinary experience gives way to extraordinary reality, and where some of the most fascinating discoveries in astronomy continue to unfold. On clear nights away from cities, where artificial lights do not overpower the stars, the Milky Way appears like a pale cloud arching across the darkness. To ancient observers, it looked almost like smoke or a glowing pathway painted across the sky. Different cultures gave it different meanings. Some imagined it as a celestial river. Others saw it as the road of spirits or the trail left by heavenly beings. Although their stories differed, nearly everyone recognized that this glowing band was something special. Today, we know that the Milky Way is not a cloud at all. It is an enormous collection of stars, gas, and dust. Since our solar system resides inside the galaxy itself, we view it from within. Looking into the Milky Way is somewhat like standing inside a giant city and trying to understand its shape by observing the countless lights surrounding you. Because we are embedded within the galaxy, the stars seem to gather into a bright strip across the sky. Interestingly, that strip becomes much brighter in one particular direction. If you observe the summer sky from the northern hemisphere, especially during the months of June, July, and August, you may notice that the Milky Way appears especially thick and luminous toward the constellations Sagittarius and Scorpius. This is not an illusion. In that direction lies the crowded central region of our galaxy. The glow becomes more intense because we are looking toward an area containing vast numbers of stars packed together over tens of thousands of light years. Yet even though the galactic center lies in that direction, no one can simply point a telescope and directly see it. Immense clouds of cosmic dust block visible light. These dark regions act almost like curtains, hiding what lies beyond. To the naked eye, portions of the Milky Way near Sagittarius actually appear interrupted by strange dark patches. Ancient people often imagined these areas as shadows or empty spaces. In reality, those dark regions are enormous clouds filled with gas and dust particles spread across unimaginable distances. Our sun occupies a relatively peaceful neighborhood located at about 26,000 light years from the galactic center. This means that when we look toward Sagittarius, we are gazing across a tremendous expanse of the galaxy. Between us and the center lie countless stars, nebulae, and interstellar clouds. Light from the hidden heart of the Milky Way must travel for 26,000 years before reaching Earth. In other words, every observation we make is also a glimpse into the distant past. The apparent position of the galactic center changes throughout the year because Earth itself is constantly moving around the sun. During certain seasons, the center is visible at night, while during others it remains hidden behind the daytime sky. Ancient civilizations carefully tracked these patterns. Without understanding the true nature of galaxies, they still recognized that certain regions of the heavens possessed unusual beauty and significance. Modern astronomers use precise coordinates to locate the center. They know exactly where it lies among the stars, even though ordinary light cannot reveal its secrets. Powerful instruments operating in radio waves, infrared light, and X-rays allow scientists to peer through the obscuring dust. These technologies transformed what once appeared to be an inaccessible mystery into one of the most carefully studied regions in the universe. It is remarkable to think that whenever you look towards Sagittarius on a dark summer evening, you are facing the very center of our galactic home. Hidden behind those beautiful star fields lies an extraordinary environment, unlike anything found near our own sun. Vast clusters of stars crowd together. Streams of gas weave through space. Powerful sources of radiation fill the region with energy. And somewhere within that hidden realm resides an object so massive that millions of stars are trapped within its gravitational influence. For countless generations, Human beings could only wonder what occupied that distant direction in the sky. They saw the glow, admired its beauty, and invented stories to explain its existence. They had no way of knowing that behind those dark clouds lay one of the greatest mysteries in astronomy. The journey toward understanding the galactic center would require entirely new ways of observing the universe, because visible light alone could never reveal what was truly hidden there. Even now, when we possess advanced observatories and powerful instruments, the center of the Milky Way remains a place of mystery and fascination. It reminds us that appearances can be deceptive. Sometimes the most extraordinary things in the universe are hidden behind curtains that only patience and curiosity can uncover. For thousands of years, long before telescopes and observatories existed, people across the world looked up into the night sky and noticed the pale band of light stretching from horizon to horizon. This glowing river of stars, now known as the Milky Way, inspired wonder in nearly every civilization that ever existed. Although no one understood its true nature, people sensed that it represented something important. It stood apart from the ordinary stars and seemed to possess a mysterious quality that invited stories, myths, and endless curiosity. Ancient observers lived under much darker skies than most people experience today. Without the glow of cities and artificial lights, the Milky Way appeared bright and detailed. Its cloudy appearance fascinated early cultures, which often interpreted the celestial band according to their own traditions and beliefs. To some, it was a heavenly road. To others, it represented a river connecting different realms. In many societies, it became associated with creation itself. The ancient Greeks believed the glowing band originated from divine events involving the gods. The Romans inherited many of these ideas and preserved them in their own traditions. Meanwhile, civilizations in Asia, Africa, and the Americas developed entirely different explanations. Despite their differences, these cultures shared one common characteristic. They all recognized that the Milky Way was not just another collection of stars. It was something unique and worthy of special attention. The Maya carefully observed the sky and incorporated celestial events into their calendars and religious practices. They saw significance in the dark lanes cutting through the Milky Way and viewed certain regions as sacred pathways. In China, astronomers recorded detailed observations of stars and celestial phenomena over many centuries. Their records became some of the earliest examples of systematic astronomy. Indigenous peoples of Australia also developed rich traditions connected to the Milky Way, sometimes focusing not on the stars themselves, but on the dark clouds that seemed to flow between them. None of these civilizations knew that they lived inside a gigantic spiral galaxy. The concept of galaxies did not yet exist. To ancient observers, the universe appeared much smaller and more intimate. Earth seemed to occupy a central position, while the heavens revolved above in orderly patterns. The stars themselves were thought to be fixed lights attached to celestial spheres surrounding the world. Even so, people noticed that the Milky Way appeared brighter in certain regions. The area near the constellation Sagittarius often stood out because of its dense concentration of stars. Although they had no understanding of galactic structure, ancient sky watchers were unknowingly looking toward the crowded central regions of the Milky Way. Hidden behind thick clouds of cosmic dust, the true heart of the galaxy remained invisible, keeping its greatest secrets concealed for thousands of years. As centuries passed, astronomers began to replace myths with careful observations. Greek thinkers such as Aristotle attempted to explain the Milky Way using natural processes. Later scholars proposed alternative ideas, though none could determine its true nature. The absence of telescopes limited human understanding. The Milky Way remained a beautiful mystery, impossible to examine in detail. Everything began to change during the 17th century. The invention of the telescope allowed observers to see that the cloudy band was actually composed of countless individual stars. One of the first people to make this realization was Galileo. Through his telescope, he discovered that the Milky Way was not a mist or vapor, but an enormous gathering of stars too numerous to count. This revelation transformed humanity's understanding of the cosmos. Even then, the center of the galaxy remained hidden. Telescopes using visible light could reveal many stars, but the dense clouds of dust lying between Earth and the galactic core blocked the view. It was like trying to observe the center of a distant city through thick fog. Astronomers could see hints of structure, but the most important region remained concealed. During the 18th and 19th centuries, scientists attempted to map the distribution of stars. Some suspected that the Milky Way possessed a flattened shape, while others imagined vast star systems extending in all directions. Yet without knowledge of the hidden core, these maps remained incomplete. Humanity had begun asking the right questions, but the answers would require technologies that had not yet been invented. Perhaps the most remarkable aspect of this long history is the patience involved. Generation after generation looked toward the same glowing band. Empires rose and fell. Languages changed. Entire civilizations disappeared. Through all of it, the Milky Way remained above, silent and unchanged, carrying secrets that would not begin to reveal themselves until the modern age. From ancient storytellers sitting beside fires to astronomers working in sophisticated observatories, humanity has shared the same curiosity. People have always wondered what lies beyond the visible world and what mysteries are hidden in the depths of the heavens, unknown to those early observers. The brightest region of the Milky Way concealed a place unlike anything they could have imagined. Deep behind curtains of dust and distance, stars crowded together by the millions. Immense clouds of gas drifted through space, and at the very center of it all rested an invisible object whose gravity governed the motions of an entire region of the galaxy. The search for that hidden center would eventually become one of the greatest scientific journeys in history, revealing that the universe was far stranger and more magnificent than any ancient myth had ever envisioned. Before humanity could understand what was hidden at the center of the galaxy, it first had to understand the galaxy itself. For most of history, people imagined the universe as a relatively small place, with Earth surrounded by stars scattered across the heavens. The idea that our sun belonged to an enormous island of hundreds of billions of stars would have seemed almost impossible to imagine. Yet, little by little, observations revealed that the Milky Way was far larger and far more complex than anyone had suspected. Our galaxy is a gigantic spiral system containing stars, planets, gas clouds, and mysterious forms of matter that cannot be directly seen. Stretching roughly 100,000 light-years across, the Milky Way is so vast that even light, traveling at nearly 186,000 miles every second, requires 100,000 years to journey from one side to the other. Such distances are difficult to comprehend because human experience offers no true comparison. Entire civilizations rise and disappear in just a few thousand years, while light itself needs far longer simply to cross our galactic home. From above, the Milky Way would appear as a graceful spiral, somewhat resembling a whirlpool or a giant pinwheel. Several curved arms extend outward from the center, wrapped around a bright and crowded core. These spiral arms are not solid structures. Instead, they are regions where stars, gas, and dust become concentrated. New stars are constantly forming inside these regions, illuminating the surrounding clouds with beautiful colors and patterns. Our own solar system resides within one of these spiral arms, known as the Orion Arm. Compared to the bustling center of the galaxy, this region is relatively quiet. The nearest stars are separated by immense distances, and our sun occupies a rather ordinary position. There is nothing particularly special about our location. In fact, astronomers often describe the sun as an average star living in an average neighborhood of an average galaxy. Yet from this modest location, humanity has managed to explore the universe through observation and imagination. The Milky Way contains several distinct regions, The thin disk forms the familiar band visible in the night sky. Most stars, including the Sun, reside within this flattened structure. Above and below the disk lies a much larger halo containing ancient stars and spherical star clusters. Surrounding everything is an enormous cloud of invisible matter whose presence can only be detected through gravity. Although scientists cannot directly observe this mysterious substance, known as dark matter, its influence extends far beyond the visible boundaries of the galaxy. At the heart of the Milky Way lies the central bulge, a densely packed region containing countless stars. Unlike the spiral arms, which are relatively thin, the bulge swells outward, forming a thick concentration of stars surrounding the galactic core. It is within this crowded region that some of the greatest mysteries of the galaxy are hidden. If one could somehow travel toward the center, the night sky would gradually change. Stars would become more numerous. Distances between neighboring stars would shrink. Nebulae and glowing gas clouds would appear more frequently. The peaceful darkness surrounding our sun would give way to a much more active and crowded environment. In some areas near the center, the sky might contain thousands of stars bright enough to cast shadows. Yet despite the richness of this region, direct observation remained impossible for centuries. Thick clouds of dust block visible light coming from the galactic core. These clouds are spread throughout the disk of the Milky Way and act almost like cosmic curtains. Looking toward the center with ordinary telescopes is similar to trying to observe a brightly illuminated city through layers of smoke and fog. Only fragments of the true picture become visible. The motion of the stars also provided clues about the galaxy structure. Astronomers discovered that the sun itself is moving through space, orbiting the galactic center at astonishing speed. Although we do not feel this motion, our solar system is racing around the Milky Way at more than 500,000 miles per hour. Even at such incredible velocity, one complete orbit requires approximately 230 million years. This means that since the age of the dinosaurs, the sun has completed only a little more than one full journey around the galaxy. Human civilization, by comparison, occupies an almost invisible fraction of a single orbit. All recorded history, from the pyramids of Egypt to the modern world, represents only a brief moment in the life of the Milky Way. As astronomers improved their understanding of galactic structure, they realized something remarkable. The center of the Milky Way was not simply another crowded region filled with stars. Something unusual seemed to exist there. The motions of stars suggested the presence of enormous mass, concentrated into a relatively small volume. Strange forms of radiation emerged from the central region. Powerful energies appeared to shape the surrounding environment. Piece by piece, evidence accumulated that the heart of the galaxy might contain something extraordinary. Yet, during the early years of astronomy, these ideas remained little more than suspicions. The hidden core continued to resist direct observation. Vast rivers of dust concealed its secrets, and the instruments available at the time were unable to penetrate the darkness. Humanity understood the broad structure of its galactic home, but the true nature of the center remained frustratingly out of reach. Still, the Milky Way itself had already revealed something profound. Our sun was not the center of the universe. Earth occupied no privileged position. Instead, we lived on a small world, orbiting an ordinary star, located far from the crowded heart of a galaxy containing hundreds of billions of suns. And somewhere, 26,000 light years away, behind curtains of dust and hidden from ordinary sight, lay the mysterious destination that generations of astronomers had only begun to suspect existed. One of the most surprising facts about the center of the Milky Way is that although it lies within our own galaxy, humanity spent thousands of years without ever seeing it directly. The hidden heart of the galaxy is not concealed by distance alone. Even though 26,000 light years is an enormous separation, the greater obstacle is something much more familiar: dust. To most people, dust is something found on shelves, furniture, or floating in sunlight near a window. Cosmic dust, however, is entirely different. It consists of incredibly tiny particles spread throughout interstellar space. These particles are composed of elements such as carbon, silicon, oxygen, and iron. Individually, they are microscopic, but together they form enormous clouds that stretch across hundreds and sometimes thousands of light years from Earth. When astronomers point ordinary telescopes toward the center of the Milky Way, they encounter these vast barriers. Visible light emitted by stars near the galactic core cannot easily pass through the countless clouds lying between us and them. The dust absorbs and scatters much of that light, creating dark regions that block our view. It is similar to attempting to observe a distant mountain range through thick fog. The mountains are still there, but the details become hidden behind the haze. This effect is so powerful that if the dust suddenly disappeared, the appearance of the night sky would change dramatically. The galactic center would shine with extraordinary brightness. Some astronomers estimate that it would appear as one of the most spectacular sights visible from Earth. The central regions of the Milky Way would dominate the heavens, revealing countless stars packed together in dazzling concentration. Instead, we see only a faint glow, interrupted by mysterious dark lanes. Ancient observers often interpreted these dark patches as empty regions. They imagined holes in the heavens or areas where stars simply did not exist. In reality, the opposite was true. Behind those dark clouds lay some of the richest and most crowded regions in the galaxy. The darkness itself was evidence that something immense lay hidden beyond. The problem became particularly frustrating for early astronomers. As telescopes improved, more and more stars became visible, yet the center remained stubbornly concealed. It was almost as though nature had placed a curtain across one of the most important regions in the galaxy. The instruments of the 17th, 18th, and 19th centuries simply could not penetrate the cosmic fog. This limitation affected humanity's understanding of the Milky Way. Without a clear view of the center, astronomers struggled to determine the galaxy's true shape. Some early maps placed the sun near the center, largely because distant stars hidden by dust could not be seen. It was only later that scientists realized the apparent distribution of stars was misleading. The galaxy was much larger than previously imagined, and our position was far from its heart. The dust itself is not evenly distributed. Some regions contain relatively little material, allowing astronomers to observe deeper into space. Other areas are extremely dense and almost completely opaque to visible light. These dark clouds can be beautiful in their own way. Against the glowing background of the Milky Way, they appear like rivers of shadow winding across the sky. Their shapes are constantly changing over millions of years as gravity and stellar winds reshape the interstellar medium. Ironically, these same clouds that obscure our view are also the birthplaces of stars. Within their cold interiors, gravity slowly gathers gas and dust together. Over time, dense regions collapse and form new suns. Entire planetary systems may emerge from these stellar nurseries. In this sense, the dust acts both as a veil hiding the galaxy's secrets and as the raw material from which future stars are created. By the early 20th century, astronomers realized that ordinary visible light alone would never reveal the galactic center. A completely different approach was necessary. Fortunately, light comes in many forms beyond those detectable by human eyes. Radio waves, infrared radiation, X-rays, and gamma rays all represent different parts of the electromagnetic spectrum. Each type of radiation interacts with matter differently, and some are capable of passing through the dust that blocks visible light. Infrared light proved especially important. Its longer wavelengths allow it to travel through dusty regions with far less interference. Objects hidden behind thick clouds suddenly became visible when observed with infrared instruments. What appeared dark and empty to the human eye transformed into crowded landscapes filled with stars. Radio waves offered another remarkable advantage. They could penetrate the dust even more effectively. By building giant radio telescopes, astronomers began listening to signals arriving from the hidden center. These invisible waves carried information that ordinary telescopes could never provide. Slowly, the dark curtain began to lift. The realization that the universe could be observed in ways beyond human vision changed astronomy forever. Human eyes evolved to survive on Earth, not to explore the cosmos. Nature had provided us with only a tiny window into reality. Technology expanded that window, revealing phenomena completely invisible to our senses. The universe suddenly became richer, stranger, and more complex than anyone had imagined. As new instruments explored wavelengths beyond visible light, unexpected discoveries began to emerge. Strange sources of radio energy appeared near the center of the galaxy. Enormous clouds of gas revealed intricate structures hidden within the darkness. Dense clusters of stars became visible for the first time. The once mysterious heart of the Milky Way slowly started to reveal itself. Yet, the deeper astronomers looked, the more mysterious the region appeared. Far from finding a peaceful concentration of stars, they uncovered an environment unlike anything surrounding our sun. Powerful forces shaped the region. Matter moved in unusual ways. Intense radiation flowed through space, and somewhere near the very center, an invisible object seemed to dominate everything around it. The darkness that had hidden the galactic core for countless generations was finally beginning to surrender its secrets. But those secrets would prove far more extraordinary than anyone had expected. Long before astronomers understood what lay at the center of the galaxy, they were confronted by an enormous obstacle spread across the Milky Way itself. The same glowing band that stretches across the night sky contains countless regions of darkness, strange shadows that interrupt the sea of stars. To ancient observers, these dark lanes appeared mysterious and almost empty. Some cultures imagined them as celestial rivers, while others believed they marked boundaries between different realms of the heavens. In reality, these dark regions are among the richest and most active places in the galaxy. The Milky Way is far from empty space. Between the stars exists an immense mixture of gas and dust known as the interstellar medium. Although the particles are spread very thinly compared with anything found on Earth, the distances involved are so enormous that tremendous clouds can form. Some of these clouds stretch across dozens or even hundreds of light years. From a distance, they become barriers capable of blocking the light from entire regions of the galaxy. Cosmic dust is made of extremely tiny grains. Many are smaller than the particles found in cigarette smoke. They contain carbon compounds, silicates, frozen water, and traces of heavier elements created inside ancient stars. These grains drift through space for millions of years, carried by stellar winds and shaped by gravity. Despite their microscopic size, they play a surprisingly important role in the life cycle of the galaxy. When light from distant stars attempts to travel through these clouds, much of it becomes absorbed or scattered. Blue light is affected more strongly than red light, which is why distant stars often appear slightly reddish. Over great distances, entire star fields disappear from view. Looking toward the center of the Milky Way, the effect becomes extreme. Layer upon layer of dust clouds stand between Earth and the galactic core, hiding one of the most fascinating regions in the universe. If a person could somehow leave the solar system and travel far above the plane of the galaxy, the appearance of the Milky Way would be astonishing. Vast dark rivers would snake through brilliant spiral arms. These shadowy lanes would contrast beautifully against billions of stars. Rather than being empty spaces, they would reveal themselves as enormous reservoirs of material from which future generations of stars are born. Inside these clouds, conditions are very different from those on Earth. Temperatures can be incredibly cold, often hundreds of degrees below zero. Sunlight barely penetrates the dense interiors. In these quiet and dark regions, gravity slowly begins its work. Tiny variations in density become larger over time. Gas and dust gather together, forming dense knots that continue to grow. Eventually, enough material accumulates for pressure and temperature to rise dramatically. A new star is born. In this sense, the dust clouds serve two roles. They hide the secrets of the galaxy, but they are also responsible for creating its future. Every atom in our bodies once belonged to ancient stars. The carbon in our cells, the oxygen we breathe, and the iron in our blood were forged in stellar furnaces long before the sun existed. Those elements were scattered into space and became part of vast clouds. From such clouds, new stars and planets emerged, including our own world. Some of the most famous objects visible through telescopes are actually enormous dust clouds illuminated by nearby stars. Nebulae such as the Eagle Nebula and the Orion Nebula reveal spectacular shapes and colors, towering columns of gas, glowing filaments, and intricate patterns demonstrate the incredible complexity hidden within these regions. Yet, even these beautiful objects represent only a small fraction of the interstellar clouds scattered throughout the Milky Way. The closer one approaches the center of the galaxy, the more abundant these clouds become. Immense concentrations of gas and dust gather there, creating one of the most complicated environments known in astronomy. Streams of matter twist through space. Powerful magnetic fields influence their motions. Shock waves generated by exploding stars ripple through the surrounding medium. Entire clusters of massive stars illuminate their surroundings with intense radiation. For many decades, these clouds frustrated astronomers. Even the largest optical telescopes could not see through them. The central regions remained hidden, leaving scientists with only fragments of information. It was like attempting to understand the layout of a great city while standing outside in thick fog. Buildings, streets, and landmarks might exist beyond the mist, but their details remained invisible. Fortunately, the universe provides more than one way of observing. While visible light struggles to penetrate dust, other forms of radiation pass through much more easily. Infrared light, with its longer wavelengths, can travel through dusty regions with relatively little interference. Radio waves perform even better. These invisible forms of light became the keys that unlocked the hidden heart of the Milky Way. As radio astronomy developed during the 20th century, astronomers began detecting signals arriving from regions that appeared completely dark to ordinary telescopes. Invisible sources of energy emerged from the center. Strange structures hidden behind the dust slowly revealed themselves. Vast clouds of hydrogen, swirling streams of gas, and unusual concentrations of stars began to appear in the data. What had once seemed like empty darkness transformed into an incredibly active and crowded environment. The shadows in the Milky Way were not signs of absence, but evidence of hidden abundance. Behind those dark curtains lay regions where stars were born, where ancient remnants drifted through space, and where some of the most powerful forces in the galaxy shaped the surrounding universe. The deeper astronomers explored these hidden regions, the more they realized that the center of the Milky Way was unlike the quiet neighborhood surrounding our sun. Conditions there were more extreme. Stars were packed closer together. Explosions were more frequent. Strange forms of energy filled the environment, and somewhere within that crowded and invisible landscape, an object of extraordinary mass and mystery waited to be discovered, silently influencing everything around it while remaining completely unseen. By the time astronomers fully understood that dust clouds were blocking the view toward the center of the Milky Way, a new question became unavoidable. If visible light could not reveal the truth, what could? The answer came from a part of nature that human eyes can never perceive directly: radio waves. Radio waves are a form of electromagnetic radiation, just like visible light, but with much longer wavelengths. These waves can travel through dense clouds of gas and dust with far less obstruction. While optical telescopes are like eyes, sensitive only to a narrow band of light, radio telescopes act more like ears, listening to the faint whispers of the universe. The development of radio astronomy in the 20th century changed everything. Suddenly, regions of the sky that had appeared completely dark were no longer silent. They began to speak in signals, patterns, and emissions that carried information about hidden structures. The center of the Milky Way, once thought to be unreachable, started to reveal its presence indirectly. One of the earliest breakthroughs came from the detection of strong radio emissions coming from the direction of the constellation Sagittarius. These signals were not random noise. They originated from a compact and highly energetic region at the very center of the galaxy. Even though no visible light could pass through the surrounding dust, radio waves carried the signature of intense activity. Radio telescopes themselves are not like traditional optical instruments. Instead of lenses or mirrors, they use large metal dishes designed to collect faint radio signals from space. Some are shaped like giant bowls, while others consist of arrays of antennas spread across large distances. By combining signals from multiple antennas, scientists can simulate a telescope much larger than any single structure on Earth. When these instruments were aimed toward the galactic center, they revealed something extraordinary. The region was not calm or empty. It was filled with motion, energy, and complexity. Clouds of hydrogen gas appeared to be orbiting an invisible point. Filaments of material twisted and stretched, moving under the influence of powerful gravitational forces. One of the most important discoveries was the presence of Sagittarius A, a strong radio source located exactly at the center of the Milky Way. This source was divided into several components, each representing different physical structures within the same region. Among them, Sagittarius A East appeared to be a supernova remnant, the remains of a massive star that exploded long ago. Sagittarius A West revealed complex streams of ionized gas spiraling inward. But the most mysterious part was Sagittarius, a star, often written as Sagittarius AE, a compact and extremely bright radio source that seemed to sit at the very heart of everything. Unlike surrounding structures, this object was incredibly small in astronomical terms, yet it emitted enormous amounts of energy. Its behavior suggested that something extremely massive and dense existed in that location. As radio observations improved, astronomers began tracking the motion of gas and stars near the center. They noticed that objects close to Sagittarius, a star, were moving at astonishing speeds. Some clouds of gas were orbiting so quickly that only a very strong gravitational force could hold them in place. The closer the observations became, the clearer it was that something invisible was controlling the entire region. At the same time, infrared astronomy provided another crucial piece of the puzzle. By observing longer wavelengths of light, scientists were able to see through the dust and detect individual stars near the galactic center. These stars were not stationary. They were orbiting around an unseen object, tracing paths that revealed its presence even though it could not be directly observed. One star in particular became especially important in this investigation. It followed a highly elliptical orbit, swinging very close to the central region before moving far away again. By carefully tracking its motion over many years, astronomers were able to measure the mass of the invisible object it was orbiting. The results were astonishing. The mass was equivalent to millions of suns, all concentrated in a region smaller than our solar system. This discovery marked a turning point in understanding the galactic center. It was no longer just a hidden region filled with dust and gas. It was the location of something far more extreme, an object so massive and compact that it could not be explained by ordinary star clusters or known forms of matter. Radio astronomy had opened a new window into the universe. Through this window, humanity began to perceive what had been hidden for so long. The center of the Milky Way was not empty. It was not quiet. It was a place of intense gravitational power, shaping the motion of everything around it while remaining invisible in ordinary light. As the data accumulated, one conclusion became increasingly difficult to avoid. At the very heart of our galaxy, there existed something far more powerful than any individual star. Something that did not shine like a star, yet influenced everything within its reach, something that could only be understood by observing its effects rather than its appearance. And this invisible presence would soon lead astronomers toward one of the most profound discoveries in modern science. As observations of the galactic center became more precise, astronomers began to notice that the region surrounding Sagittarius, a star, was not only active, but unusually crowded with unusual structures. This was not a calm environment where stars drifted peacefully through space. Instead, it resembled a tightly packed cosmic city where motion, energy, and gravity constantly interacted in complex ways. Near the center of the Milky Way, stars are packed far more densely than in the region around our sun. If the solar neighborhood were a quiet countryside with wide open space between houses, the galactic center would be a dense metropolis where buildings stand close together and movement is constant. Distances that take light years in our region shrink dramatically closer to the core, and gravitational interactions become much more frequent. One of the most striking discoveries in this region is the presence of young, massive stars. Under normal expectations, the center of the galaxy should be a difficult place for new stars to form. Strong gravitational forces, intense radiation, and turbulent gas flows should make stable star formation rare. Yet astronomers have found clusters of extremely bright and massive young stars orbiting very close to Sagittarius, a star. Their existence raises deep questions about how star formation can occur in such extreme conditions. These stars are not only young, but also unusually large and short-lived. Massive stars burn through their fuel quickly, living only a few million years compared to the billions of years typical for smaller stars like the Sun. Their presence near the galactic core suggests that star formation has been occurring there relatively recently. On cosmic timescales, this indicates that the center of the Milky Way is not just a static structure, but a continuously evolving environment. In addition to young stars, astronomers have observed enormous clouds of gas moving in complex and sometimes chaotic patterns. Some of these clouds appear to be streaming inward toward the central region, while others are being pushed outward by energetic processes. The motions of this material are not random. They are shaped by powerful gravitational forces and possibly by energetic events occurring near the center. Among the most fascinating features are what appear to be gas streams orbiting very close to the central object. These streams move at extremely high speeds, sometimes reaching thousands of kilometers per second. At such velocities, even small changes in direction or energy can have dramatic effects. The behavior of these gas structures provides important clues about the nature of the unseen mass at the core. Astronomers have also identified regions of intense radiation near the center. X-rays and gamma rays emerge from compact sources, indicating that extremely energetic processes are taking place. These forms of radiation are not produced by ordinary stars alone. They suggest the presence of matter being heated, compressed, or accelerated to extreme conditions. One of the most intriguing observations involves the so-called mini-spiral structure near Sagittarius, a star. This structure consists of streams of ionized gas, forming a pattern that resembles a spiral as it moves inward. The gas appears to be gradually falling toward the center, guided by gravitational forces. However, not all of it reaches the central object. Some of it is redirected or expelled, suggesting the presence of complex interactions that regulate the flow of material. Within this chaotic environment, astronomers have also detected strong magnetic fields. These invisible forces influence the motion of charged particles, shaping the structure of gas clouds and contributing to the formation of large-scale patterns. Magnetic fields in the galactic center are much stronger and more complex than those found in the region surrounding our sun. Despite the chaos, there is also a sense of underlying order. Many of the observed motions follow predictable paths, especially those of stars orbiting the central region. These orbits provide some of the most important evidence about what lies at the very heart of the galaxy. By tracking these movements over time, astronomers can reconstruct the gravitational landscape of the hidden core. Some stars follow long, elongated orbits that take them very close to the center before swinging far away again. During their closest approach, these stars move at incredible speeds, revealing the strength of the gravitational pull they are experiencing. These observations make it increasingly clear that the central region contains an object or collection of mass that is both extremely dense and extremely powerful. Yet even with all this activity, one feature remains consistent. The central object itself cannot be seen directly. It does not emit visible light in a way that would allow it to be observed like a normal star. Instead, its presence is inferred entirely through its effects on surrounding matter. Stars orbit something invisible. Gas streams respond to something unseen. Energy radiates from a region where no ordinary object can be identified. This combination of invisibility and overwhelming influence is what makes the galactic center so mysterious. It is not defined by what we can see, but by what we can measure indirectly. And as observations continue to improve, the evidence points more strongly toward a single extraordinary conclusion. At the heart of the Milky Way, something exists that defies ordinary expectations, something so massive and compact that it reshapes everything around it while remaining hidden from direct view. As astronomers continued studying the center of the Milky Way, they discovered that it is not only dominated by invisible forces, but also surrounded by some of the most extreme star clusters in the galaxy. These clusters are dense groups of stars bound together by gravity, often containing thousands or even millions of individual suns packed into relatively small regions of space. In most parts of the Milky Way, stars are separated by enormous distances. The nearest star to our sun is more than 4 light years away, which is already difficult to imagine. But near the galactic center, the situation is dramatically different. In some star clusters close to Sagittarius, stars can be separated by distances measured in fractions of a light year. If you were standing on a hypothetical planet in such a region, the night sky would be filled with bright stars so close and numerous that darkness would almost disappear entirely. One of the most famous structures in this region is the nuclear star cluster, a dense and complex collection of stars surrounding the very core of the galaxy. This cluster is not uniform. It contains stars of different ages, compositions, and sizes. Some are ancient, having formed billions of years ago. Others are relatively young, having formed within the last few million years. This mixture suggests that star formation in the galactic center has occurred repeatedly over long periods of time. The environment inside these clusters is shaped by powerful gravitational forces. The closer one moves toward the center, the stronger the gravitational pull becomes. This affects not only the motion of stars, but also the behavior of gas clouds and dust. Material is constantly being pulled, compressed, and redistributed, creating a dynamic and ever-changing environment. Despite these harsh conditions, stars continue to form. Dense clouds of gas collapse under gravity, igniting nuclear fusion and creating new suns. However, the process is more chaotic than in quieter regions of the galaxy. Interactions between nearby stars can disrupt forming systems, and intense radiation from massive stars can strip away material from young stellar objects. As a result, many stars in this region do not have stable planetary systems like our own. Among the most intriguing discoveries are clusters containing extremely massive stars. These stars are far larger and brighter than the sun, often tens or even hundreds of times more massive. Their lifespans are short in cosmic terms, burning through their fuel rapidly before ending in spectacular supernova explosions. When these stars die, they enrich the surrounding environment with heavy elements, contributing to the cycle of matter that shapes future generations of stars. The presence of such massive stars near the galactic center raises interesting questions about how they formed in such a turbulent environment. In most regions of the galaxy, massive star formation is relatively rare. Yet near the center, conditions seem to favor the creation of large, short-lived stars. This suggests that the environment itself plays a significant role in determining the types of stars that form. The interaction between star clusters and the central gravitational source is particularly important. As clusters orbit the galactic center, they are influenced by tidal forces, which stretch and distort them over time. Some stars are pulled away and become isolated, while others are driven closer to the center. This constant reshaping creates streams of stars and complex orbital patterns that trace the gravitational influence of the unseen central mass. In some cases, entire clusters may be disrupted as they approach the core. The gravitational pull becomes so strong that the cluster loses its structure, scattering stars across different orbits. This process contributes to the dense and chaotic environment observed near Sagittarius, a star. One of the most fascinating aspects of these clusters is how they act as natural laboratories for studying extreme physics. Conditions near the galactic center cannot be replicated on Earth. Gravity is stronger, radiation levels are higher, and interactions between objects occur more frequently. By observing these regions, astronomers can test theories about how matter behaves under extreme conditions. Infrared observations have been especially important in revealing these star clusters. Because dust blocks visible light, infrared telescopes are necessary to see through the obscuring material. These observations have uncovered stars that were previously invisible, allowing scientists to map the structure and motion of clusters in unprecedented detail. As data improves, it becomes increasingly clear that the galactic center is not a uniform or simple environment. Instead, it is a layered system of interacting structures. Star clusters orbit the central region. Gas clouds flow through magnetic fields. Radiation fills the surrounding space. And at the very center, everything appears to be governed by an invisible source of enormous mass. This central source does not behave like a normal star or cluster. It does not shine invisible light. It does not move in the same way as surrounding objects. Instead, it exerts a gravitational influence so strong that it shapes the entire region around it. The more astronomers observe, the more this invisible presence stands out as the defining feature of the galactic core. The giant star clusters, with all their beauty and chaos, are therefore not isolated systems. They are part of a much larger structure, all orbiting and interacting within the influence of something far more massive than anything visible nearby. And as the story of the galactic center continues to unfold, these clusters provide some of the clearest clues yet about what truly lies hidden at the heart of the Milky Way. Deep within the central region of the Milky Way, beyond the dense star clusters and crowded stellar neighborhoods, lies a vast and constantly shifting network of gas and dust. These structures are not static. They move like rivers across space, flowing under the influence of gravity, pressure, radiation, and magnetic fields. To an observer with the ability to see the galaxy from afar, the center would appear less like a solid object and more like a living, breathing system of motion and change. Interstellar gas is primarily composed of hydrogen, the simplest and most abundant element in the universe. Mixed within it are traces of helium and heavier elements created in the cores of ancient stars. This material is spread so thinly that in many regions of space, it would be considered a vacuum by Earth standards. Yet over vast distances, this thin gas accumulates into enormous clouds that can stretch across hundreds of light years. Near the galactic center, these clouds become especially complex. They are compressed by the immense gravitational pull of the central region and shaped by energetic processes that are far more intense than those found in the outer parts of the galaxy. As a result, the gas does not remain evenly distributed. Instead, it forms filaments, streams, arcs, and spiraling structures that twist and bend through space. Some of these gas streams appear to be moving inward, gradually falling toward the center of the galaxy. Others are being pushed outward by energetic events, possibly linked to stellar explosions or radiation from compact sources near Sagittarius, a star. This constant movement creates a dynamic balance between inflow and outflow, giving the central region a turbulent and ever-changing character. One of the most striking features observed by astronomers is the presence of long, thin filaments of gas that stretch across vast distances. These filaments often follow curved paths, suggesting they are being guided by strong magnetic fields. In some cases, they appear to connect different regions of the galactic center, acting like invisible threads weaving the structure of the inner galaxy together. Magnetic fields in this region are significantly stronger than those found near our solar system. Although invisible, they exert a powerful influence on charged particles within the gas. As particles move along these fields, they trace out complex patterns that reveal the underlying structure of the environment. Without magnetic fields, the gas would behave very differently, and many of the observed structures would not exist. Within these cosmic rivers, density variations play a crucial role. When regions of gas become slightly denser than their surroundings, gravity begins to pull more material into them. Over time, these regions can grow into dense clouds capable of forming new stars. This process is slow by human standards, often taking millions of years, but it is fundamental to the evolution of the galaxy. However, the environment near the galactic center is not always gentle. Shock waves generated by supernova explosions travel through the gas, compressing and heating it. These shock fronts can trigger star formation in some regions while disrupting it in others. The result is a complex interplay between creation and destruction, where new stars are born even as existing structures are torn apart. Infrared and radio observations have revealed that some of these gas clouds are moving at extremely high speeds. In certain regions, gas is accelerated to hundreds or even thousands of kilometers per second. Such extreme motion suggests that powerful forces are acting on the material, most likely connected to the gravitational influence of the central object and energetic processes occurring nearby. Despite the chaotic appearance, there is a hidden structure to this motion. Gas does not move randomly. It follows gravitational paths, magnetic field lines, and pressure gradients. When mapped carefully, these flows reveal a structured environment shaped by the deep gravitational well at the center of the galaxy. Everything seems to orbit, spiral, or stream toward a common focal point. This focal point remains invisible in ordinary light, yet its influence is unmistakable. Gas clouds curve as they approach it. Stars adjust their orbits in response to it. Even the shape of the surrounding environment appears molded by its presence. The more data astronomers collect, the clearer it becomes that something extremely massive lies at the heart of these motions. In some regions close to Sagittarius, a star, gas becomes so ionized that it emits strong radio waves. This ionized gas forms glowing structures that trace the outline of energetic processes occurring near the center. These emissions provide some of the most detailed information about conditions in otherwise hidden regions. Over time, the study of these gas rivers has transformed our understanding of the galactic center. What once appeared to be a simple, dark region has revealed itself as a highly active and structured environment. The gas flows act as both a record and a map, showing how matter moves and evolves under extreme gravitational influence. And as astronomers continue to trace these cosmic currents, they are drawn ever closer to the same conclusion that emerges from every other line of evidence. All motion, all structure, and all energy in this region seem to converge toward a single hidden source, waiting silently at the center of the Milky Way, shaping everything around it without ever being directly seen. As astronomers refine their observations of the galactic center, one particular region began to stand out from everything else. It was not a star cluster, not a cloud of gas, and not a diffuse glow. It was a compact, extremely bright radio source located precisely at the heart of the Milky Way. This object would come to be known as Sagittarius A, a name that would eventually become central to the understanding of our galaxy. The designation itself reflects how astronomical naming works. Sagittarius refers to the direction in the sky where the object appears, while the letter A marks it as the strongest radio source in that region. At first, it was not clear that Sagittarius A was a single object. Early radio observations suggested a complex structure with multiple overlapping sources of emission. Over time, higher resolution measurements revealed that this region could be separated into distinct components, each with different physical origins. One of these components appeared to be the remnant of a supernova explosion, known as Sagittarius A East. It consists of expanding gas and debris left behind when a massive star reached the end of its life. This structure emits radio waves as the shock wave from the explosion interacts with surrounding material. It provides important evidence that the galactic center has experienced violent stellar events in relatively recent cosmic history. Another component, Sagittarius A West, revealed a more intricate structure. It consists of ionized gas streams arranged in complex shapes that resemble arms or spiral patterns. These structures are shaped by gravitational forces and magnetic fields, and they appear to be slowly moving inward toward the central region. This flow of material suggests that the galactic center is not static, but actively interacting with its environment. However, the most important discovery was a compact and extremely bright source at the very core, known as Sagittarius, a star. Unlike the surrounding structures, this object is remarkably small in size compared to the scale of the galaxy, yet it emits a significant amount of energy, particularly in radio wavelengths. Its compactness and intensity immediately made it an object of intense scientific interest. As technology improved, astronomers were able to observe Sagittarius, a star, with increasing precision. Very long baseline interferometry allowed multiple radio telescopes across the Earth to function together as a single enormous instrument. This technique provided the sharpest possible view of the galactic center in radio light. Even with this level of detail, Sagittarius, a star, remained unresolved as a point-like source, meaning it could not be broken down into visible structure. This was a crucial clue. If an object is both extremely compact and extremely massive, yet does not emit visible light like a normal star, it suggests that something fundamentally different is occurring. Ordinary star clusters would not remain so tightly packed without collapsing or dispersing. The only explanation consistent with the observations was that an enormous amount of mass was concentrated into a very small region of space. Further infrared observations supported this conclusion. By tracking the motion of stars very close to Sagittarius, a star, astronomers discovered that they were orbiting an invisible center. These stars followed highly elliptical paths, moving at incredible speeds when near their closest approach. Their orbits could only be explained if they were responding to a gravitational force equivalent to millions of times the mass of the Sun. The most famous of these stars became a key piece of evidence. Over many years of observation, its complete orbit was mapped with remarkable precision. At its closest point, it came extremely near to the central region, moving so fast that its motion provided a direct measurement of the mass contained within that invisible area. The results were consistent across multiple independent studies. What made Sagittarius, a star, so important was not just its brightness in radio wavelengths, but its role as the gravitational anchor of the entire central region. Everything around it, including gas clouds, star clusters, and individual stars, appeared to be orbiting or influenced by this single point. Yet the object itself remained unseen in visible light. This combination of invisibility and overwhelming gravitational influence led to a major shift in how scientists understood the galactic center. It was no longer sufficient to describe the region as simply dense or active. Instead, it had to be understood as the location of an extremely compact and massive object that dominated its surroundings through gravity alone. Sagittarius, a star, became the focal point of decades of further research. Each new observation added another piece to the puzzle. Variations in radiation, sudden flares of energy, and subtle changes in surrounding gas behavior all pointed toward a highly energetic environment near the central object. Yet despite all this activity, the object itself remained hidden from direct optical view. As the evidence accumulated, the picture became clearer. Sagittarius, a star, was not just another astronomical source. It was the key to understanding the entire structure and behavior of the galactic center, and its true nature would eventually lead to one of the most profound realizations in modern astronomy, a realization that would redefine what lies at the very heart of the Milky Way. Understanding what lies at the center of the Milky Way required more than just observing strange radio signals or tracking unusual star motions. Astronomers also needed to know something much more fundamental. How far away is it? Without an accurate distance, every measurement of size, mass, and energy would remain uncertain. Like trying to understand a landscape through a blurred window without knowing how close or far it is. The distance to the galactic center turned out to be one of the most carefully studied numbers in modern astronomy. It is not measured directly like distances on Earth. Instead, it is built from multiple layers of indirect evidence, each supporting the others. Over decades, scientists refined this value using different methods, each relying on different physical principles. One of the earliest approaches involved studying the distribution of globular clusters. These are ancient, spherical groups of stars that orbit the Milky Way in a halo surrounding the galaxy. By mapping their positions in space, astronomers noticed that they were not centered around Earth, but instead formed a pattern suggesting a distant central point. This provided the first strong evidence that the true center of the galaxy was far away in the direction of Sagittarius. Later, variable stars known as Cepheids became important tools. These stars changed their brightness in a regular and predictable way. By comparing their true brightness with how bright they appear from Earth, astronomers can calculate their distance. Using Cepheids located in different parts of the galaxy, scientists gradually built a three-dimensional map of the Milky Way. This map consistently pointed toward a central region located tens of thousands of light years away. As technology improved, infrared observations provided even more precise measurements. Since infrared light can pass through the dust that blocks visible light, it became possible to observe stars much closer to the galactic center. By measuring their positions and motions, astronomers refined their understanding of the galaxy's structure. These observations confirmed that the Sun is not located near the center, but instead resides in a distant spiral arm. Another powerful method involves studying the orbits of stars near Sagittarius, a star. These stars move in well-defined paths under the influence of the central gravitational source. By carefully tracking their motion over time, astronomers can apply the laws of gravity to determine the scale of the system. The size of the orbits, combined with their periods, provides a natural way to estimate distance. Each independent method converged on a similar result. The center of the Milky Way is located approximately 26,000 light years from Earth. In more precise measurements, the value is refined to within a small margin of uncertainty, but the general scale remains the same. This number is not just a technical detail. It represents the scale of our place in the galaxy and defines the structure of everything we observe around us. To put this distance into perspective, light itself takes 26,000 years to travel from the galactic center to Earth. This means that when we observe the center today, we are actually seeing it as it was in the distant past. Any changes occurring there now will not be visible to us for tens of thousands of years. This delay in observation creates a kind of cosmic time separation. The galaxy is not observed as it is in a single moment, but as a layered history, Different regions are seen at different points in their past, depending on how far away they are. The center of the Milky Way, therefore, is not only a place in space, but also a window into deep time. Knowing the distance also allowed astronomers to estimate the true size and energy of the central region. Once the scale was understood, the motions of stars and gas clouds revealed something extraordinary. The central mass was far too large to be explained by normal star clusters. It had to be something far more compact and dense than anything previously observed. This realization connected directly to earlier discoveries about Sagittarius, a star. If the distance was correct, then the amount of mass concentrated in the central region implied an object of extreme density, an object that could not be seen directly, yet whose gravitational influence dominated everything nearby. With distance established, the galactic center became more than a mysterious glow hidden behind dust. It became a precisely measured region of space with known scale, structure, and dynamics. Every orbit, every gas flow, and every radiation source could now be interpreted within a consistent framework. Still, one question remained unanswered. What exactly was capable of concentrating so much mass into such a small region while remaining invisible in ordinary light? The answer to that question would gradually emerge from the behavior of stars orbiting the unseen center, leading astronomers toward one of the most important discoveries in the entire history of science. Once the distance to the center of the Milky Way was established, astronomers could finally begin translating observations into physical reality. The motions of stars near Sagittarius, a star, were no longer just interesting patterns. They became measurements of mass, gravity, and structure on a galactic scale. What emerged from this analysis was something extraordinary. The center of our galaxy appeared to contain an object with the mass of millions of suns, compressed into a region smaller than our solar system. The key evidence came from tracking individual stars as they moved through their orbits. Unlike stars in most regions of the galaxy, which follow relatively stable and slow paths, these central stars move at extreme speeds. Some of them reach thousands of kilometers per second when they approach their closest point to the center. Their trajectories are not random. They are precise, predictable, and governed by a single dominant gravitational source. One of the most important observations involved a star that completed a full orbit around the central region within a human lifetime of study. By carefully recording its position year after year, astronomers were able to map its complete path. The orbit was highly elliptical, meaning the star swings in very close to the center before traveling far outward again. At its closest approach, it experiences an intense gravitational pull that dramatically increases its speed. Using these orbital measurements, scientists applied the laws of gravity developed by Isaac Newton and later refined by Albert Einstein. These laws allow mass to be calculated based on orbital motion. The results consistently pointed to the same conclusion. The amount of mass required to hold these stars in their observed orbits was far too large to be explained by any known cluster of stars or ordinary matter. If the mass were spread out among many stars, the region would behave differently. Stars would interact more frequently, and the overall structure would be unstable. Instead, what is observed is a compact, organized system where stars orbit a single central point with remarkable precision. This strongly suggests that the mass is concentrated in an extremely small volume. As observations improved, astronomers pushed their measurements even closer to the center. They found that some stars approach within a very small fraction of a light year from Sagittarius, a star. Even at these distances, the gravitational influence remains consistent with a single massive object. No visible source of light or matter can account for such extreme conditions. At the same time, the central region shows very little visible emission from ordinary stars at the exact location of this mass concentration. This absence of light is just as important as the presence of motion. If millions of stars were packed into such a small region, the area would be extremely bright. Instead, it remains relatively dark in visible wavelengths, suggesting that the mass is not in the form of normal stars. Combining these lines of evidence leads to a powerful conclusion. The central object must be extremely compact, extremely massive, and largely invisible in ordinary light. These are exactly the characteristics predicted for a supermassive black hole. A black hole is not an object in the traditional sense. It is a region of space where gravity is so strong that nothing, not even light, can escape once it crosses a boundary known as the event horizon. While black holes were first predicted theoretically through the equations of general relativity, their existence was long debated. The galactic center provided one of the strongest real-world cases supporting their existence. The term supermassive refers to black holes that are millions or even billions of times more massive than the Sun. These objects are thought to exist at the centers of most large galaxies. In the case of the Milky Way, the central black hole is relatively quiet compared to others in the universe, but its gravitational influence is unmistakable. One of the most compelling aspects of this evidence is its consistency across different methods. Whether astronomers use stellar orbits, gas dynamics, or radio observations, they arrive at the same conclusion. All paths point toward a single compact source of immense gravity located at Sagittarius, a star. Even more convincing is the stability of the system. The stars near the center have been observed for decades, and their motions remain consistent with a central mass that does not move or drift significantly. This stability is exactly what would be expected from a supermassive black hole anchoring the galactic center. However, despite this strong evidence, a black hole cannot be seen directly. It does not emit light in the way stars do. Instead, its presence is inferred through its effects on surrounding matter. Gas heats up as it falls toward the center. Stars accelerate as they pass near it. Radiation is emitted from the environment around it, but the object itself remains hidden. This combination of invisibility and overwhelming influence makes the galactic center one of the most fascinating regions in the universe. It is a place where the limits of observation are reached, and where the laws of physics must be used to understand what cannot be directly seen. As the evidence continues to accumulate, the picture becomes increasingly clear. At the heart of the Milky Way lies an object of immense gravity, shaping the motion of everything around it. And while it cannot be observed directly, its presence is written across the sky in the orbits of stars, the flow of gas, and the structure of the central galaxy itself. After the idea of a supermassive black hole became the leading explanation for the center of the Milky Way, astronomers shifted their focus to something even more powerful than theory: long-term observation. If such an invisible object truly existed, then the stars near it should behave like test particles in a gravitational field. Their motions would reveal the shape, mass, and position of the unseen center with increasing precision over time. Near Sagittarius, a star, astronomers found exactly what they were looking for: a group of stars moving in tight, fast, and highly curved orbits around a single point in space that emits no visible light. These stars are often called S-stars, and they are among the most important tools ever used to study the galactic center. At first glance, the region seems chaotic. Dozens of stars move in different directions, each following its own path through space. But when their motions are tracked carefully over many years, a clear pattern emerges. All of them are orbiting something extremely small and extremely massive. Not a cluster, not a nebula, not a visible object, but a single dominant gravitational source. One of these stars became especially important in confirming this picture. It follows a very elongated orbit, meaning it travels far out from the center before diving back in toward the invisible mass. At its closest approach, it moves at an extraordinary speed, far faster than any star in the outer regions of the galaxy. At its farthest point, it slows down and arcs away, only to return again in a repeating cycle. The shape of this orbit is not random. It is precisely what would be expected if the star were moving under the influence of a massive compact object. Exactly as predicted by Einstein's, the curvature of space itself becomes noticeable near the center, subtly altering the star's path over time. By tracking these orbits year after year, astronomers have been able to map the gravitational field of the galactic center with remarkable accuracy. Each star acts like a probe, tracing the invisible structure that surrounds Sagittarius, a star. Together, they form a kind of natural laboratory for studying gravity under extreme conditions. What makes these observations so powerful is that they leave very little room for alternative explanations. A cluster of ordinary stars could not remain so tightly packed without collapsing or dispersing. Dark gas clouds could not produce such stable, repeating orbits. Only a single massive object concentrated in a very small region can account for the data. As measurements improved, astronomers were able to pinpoint the exact location of the central mass. It aligns with the radio source Sagittarius, a star, to within extremely small margins of error. This means that the invisible gravitational center and the compact radio emission are not separate objects, but different manifestations of the same central region. The stars closest to this region experience the most extreme conditions. Their orbits bring them into areas where gravitational forces are strong enough to significantly affect time itself. According to relativity, time passes more slowly in stronger gravitational fields. Near the galactic center, this effect becomes measurable, adding another layer of complexity to the environment. Despite these extreme conditions, the stars remain intact. They are not torn apart, at least not yet, because their orbits keep them just far enough away from the central singularity. However, their paths are constantly evolving. Small perturbations accumulate over time, slowly reshaping their trajectories. In cosmic terms, these changes are subtle, but over thousands of years, they become significant. Some stars appear to form loose groups that move together for a time before separating. Others pass close to each other, exchanging energy through gravitational interaction. Yet, through all of this motion, the central point remains dominant, unchanged, and invisible. The deeper astronomers look, the more the galactic center resembles a carefully orchestrated system. It is not random chaos, but a structured environment governed by a single massive anchor. Everything in the region responds to this anchor, whether it is gas, dust, or individual stars. These orbital observations also provide one of the most direct ways of measuring the mass of the central object. By applying gravitational equations to the observed paths, scientists consistently arrive at a value of about 4 million times the mass of the Sun. All of this mass is confined to a region so small that it would fit well within the orbit of Mercury. This combination of enormous mass and tiny volume is what defines a supermassive black hole. It is not seen directly, but its presence is unavoidable. The stars themselves trace its outline in motion, like glowing markers circling an invisible point in space. As long-term observations continue, the picture becomes more refined but not fundamentally changed. The central object remains unseen, yet overwhelmingly influential. The stars continue their silent orbits around it, repeating paths that reveal the structure of a region no human eye can directly observe. In this way, the galactic center is not just discovered through images, but through motion itself. The stars do not simply exist near it. They describe it, define it, and confirm it, one orbit at a time, around the invisible giant at the heart of the Milky Way. As the story of the galactic center becomes clearer, attention naturally moves closer to the most extreme boundary in this entire system. The region surrounding the supermassive black hole is not uniform or calm. It is layered, structured, and full of physical limits that begin to reshape how matter behaves. The most important of these boundaries is the event horizon. The event horizon is not a surface in the traditional sense. It is a mathematical boundary in space that separates what can escape from what cannot. Once matter or light crosses this boundary, it is no longer able to return. From the outside, it appears as a silent point of no communication, where signals fade into nothingness. From the inside, the rules of return simply no longer exist. Near this boundary, the environment becomes increasingly extreme. Gas clouds that drift too close begin to accelerate rapidly. They do not fall straight in like simple objects on Earth. Instead, they spiral inward, forming flattened structures known as accretion flows. These flows rotate at enormous speeds, heating up as friction and compression increase their energy. As the gas heats, it begins to emit radiation across multiple wavelengths. Some of this radiation is in infrared light, some in radio waves, and some in X-rays. This is why regions near Sagittarius, a star, appear active, even though the black hole itself does not emit light. What we observe is not the object directly, but the energy released by matter interacting with it. The closer material gets to the event horizon, the more dramatic these effects become. Time itself begins to behave differently. According to general relativity, strong gravity slows the passage of time relative to distant observers. This means that from far away, anything falling toward the event horizon appears to slow down as it approaches the boundary. The light it emits becomes increasingly red-shifted and faint. From the perspective of the falling material, however, the experience is different. It continues its inward motion without noticing anything unusual at first. The changes become noticeable only as gravitational forces grow stronger and tidal effects increase. These tidal forces stretch objects in the direction of gravity while compressing them in other directions, a process sometimes described as spaghettification. However, near a supermassive black hole like Sagittarius, a star, these tidal forces at the outer edge are relatively gentle compared to smaller black holes. This is because the event horizon of a supermassive black hole is much larger, meaning the gradient of gravity changes more gradually at the boundary. As a result, matter can cross the event horizon without immediately being torn apart, although its fate remains sealed. Inside the surrounding region, matter forms a complex structure of inflowing streams and turbulent flows. Magnetic fields twist through this material, guiding charged particles along curved paths. Collisions between particles generate heat and radiation, creating a glowing environment around the otherwise invisible core. This region is sometimes described as a hot plasma environment shaped by extreme gravity and magnetism. Occasionally, the galactic center experiences flares, sudden bursts of energy that briefly increase its brightness in X-ray and infrared wavelengths. These flares are thought to be caused by small amounts of material falling into the inner regions or interacting with magnetic field lines in unstable configurations. Although dramatic, these events are relatively small compared to the total mass of the black hole. Despite all this activity, the event horizon itself remains hidden. No light escapes from within it. No signal can cross outward once it has passed the boundary. This is what makes black holes fundamentally different from any other object in the universe. They are defined not by what they emit, but by what they prevent from escaping. The region just outside the event horizon is sometimes called the photon sphere, where light can orbit the black hole in unstable paths. In theory, photons can circle the black hole before eventually either escaping or falling inward. This creates a region where the geometry of space is so strongly curved that even light follows closed or near-closed trajectories. If one could observe the galactic center from a closer vantage point, the sky would appear distorted. Background stars would be warped by gravitational lensing, their light bent around the massive central object. This effect is a direct consequence of space itself being curved by mass and energy. All of these phenomena combine to create a layered structure. Far from the black hole, stars orbit calmly in predictable paths. Closer in, gas becomes turbulent and heated. Nearer still, radiation intensifies, and time distortion becomes significant. Finally, At the event horizon, all classical notions of escape end completely. Even with all this complexity, one thing remains consistent. The black hole itself is never directly seen. It is always inferred, always reconstructed from the behavior of its surroundings. The event horizon is not a visible edge, but a limit defined by physics itself. As understanding deepens, the galactic center becomes less like a mysterious void and more like a structured system with clear physical rules. Yet, at its core remains something that cannot be directly accessed, a boundary beyond which information does not return, and where the known universe meets its most absolute limit. As we move closer to understanding the center of the Milky Way, it becomes impossible to separate space from time. Near a supermassive black hole, gravity is not just a force that pulls objects inward. It becomes a shaping influence on time itself, altering how moments pass depending on where you are in the gravitational field. At a distance like the one between Earth and the galactic center, time flows normally for us. Our clocks tick steadily, our days pass in familiar rhythm, and the motion of stars appears predictable. But as one approaches Sagittarius, a star, the environment begins to change in subtle but profound ways that only become noticeable through careful measurement. According to the theory of general relativity, gravity affects time because massive objects curve the structure of space and time together. This curvature means that time runs slightly slower in stronger gravitational fields compared to weaker ones. The difference is small near Earth, but near a black hole, it becomes significant. For stars orbiting close to the central mass, this effect means their internal processes, orbital timing, and even the light they emit are influenced by the intense gravitational environment. From a distant observer's perspective, these stars appear to move through time at a slightly different rate compared to objects farther away in the galaxy. This time difference becomes especially important when tracking the orbits of stars near Sagittarius, a star. Astronomers must account not only for spatial motion, but also for relativistic effects that alter the timing of signals received on Earth. Without these corrections, the calculated orbits would not match observations. As stars approach closer to the central region, their velocities increase dramatically. In extreme cases, they reach a significant fraction of the speed of light. At such speeds, another relativistic effect becomes important: time dilation caused by motion itself. This means that time slows down not only because of gravity, but also because of velocity. The combination of gravitational time dilation and velocity-based time dilation creates a complex environment where different observers experience time in slightly different ways. A star moving rapidly near the black hole experiences time differently than a distant observer watching from the outer regions of the galaxy. One of the most fascinating consequences of this is how signals from the central region are perceived. Light emitted from stars or gas near the black hole becomes stretched as it climbs out of the gravitational field. This process, known as redshift, shifts the light toward longer wavelengths, making it appear dimmer and less energetic to distant observers. In extreme cases, light can be so strongly redshifted that it effectively disappears from visible detection. This contributes to the invisibility of the central object itself. Even if light is emitted near the event horizon, it may never reach observers in a form that can be detected. These effects combine to create a layered perception of reality around the galactic center. To an observer far away, events near the black hole appear slowed down, dimmed, and distorted. To an observer closer in, the same events would feel completely normal, governed by local physical laws that remain consistent. This difference in perspective highlights one of the most important ideas in modern physics. Time is not universal. It is not the same everywhere in the universe. Instead, it is flexible and dependent on the environment in which it is measured. Near Sagittarius, a star, this flexibility becomes especially noticeable. The orbits of stars provide natural clocks that reveal how time behaves under extreme conditions. By comparing predictions from relativity with actual observations, astronomers have confirmed that time behaves exactly as Einstein's theory predicts, even in the strongest gravitational fields found in our galaxy. Despite these extreme conditions, the structure of the system remains stable over long periods of time. Stars continue their orbits, gas continues to flow, and the central mass remains dominant. This stability suggests that even in such an intense environment, the laws of physics remain consistent and predictable. However, the closer one imagines approaching the event horizon, the more unfamiliar the concept of time becomes. From a distant perspective, objects falling toward the black hole appear to slow down indefinitely, never quite crossing the boundary. Their light becomes fainter and redder, eventually fading beyond detection. From the perspective of the falling object, the journey continues without such dramatic effects at first. But as the limit of the event horizon is approached, the structure of space-time itself becomes so strongly curved that normal intuition begins to fail. Time and space begin to exchange roles in ways that challenge everyday understanding. These ideas reveal why the center of the Milky Way is not just a physical location, but also a region where fundamental concepts like time, motion, and causality behave in deeply interconnected ways. It is a place where the universe reveals the limits of ordinary experience and shows how flexible reality can be under extreme conditions. And as observations grow more precise, each new measurement continues to confirm that even in the most extreme environment in our galaxy, the laws of physics remain consistent, guiding everything from the smallest particle to the vast orbiting stars that silently trace the presence of the invisible giant at the center. When imagining the center of the Milky Way, it is natural to think only about stars, gas clouds, and black holes. Yet another question often appears in the background of all this physics. Could anything survive there? Could any form of structure, chemistry, or even life exist in such an extreme environment? The region around Sagittarius, a star, is one of the most hostile environments in the galaxy. It is filled with strong radiation, rapid stellar motion, dense star clusters, and powerful gravitational effects. Even so, it is not a uniform field of destruction. Instead, it is a layered environment where conditions change dramatically depending on distance from the central object. Farther out from the center, in the broader nuclear star cluster, conditions are intense but not completely unmanageable on cosmic scales. Stars are closer together than in the solar neighborhood, but still separated by distances large enough that direct collisions are rare. Planetary systems could theoretically exist in such regions, although they would experience frequent gravitational disturbances from nearby stars. As one moves closer toward Sagittarius, a star, the environment becomes increasingly difficult for stable systems. Strong radiation from massive stars and energetic events bathes the region in high-energy light. X-rays and ultraviolet radiation can strip atmospheres from planets and disrupt complex chemistry. Any potential surface environment would be continuously exposed to extreme energy input. Gas and dust in this region are constantly influenced by shock waves and magnetic activity. These processes can both destroy and create molecular structures. In some areas, complex organic molecules have been detected within interstellar clouds. This suggests that even in harsh environments, chemistry can become surprisingly rich. However, the transition from chemistry to stable long-term environments remains highly uncertain. The gravitational environment near the central black hole adds another layer of complexity. Strong tidal forces can destabilize orbits, pulling objects into highly elliptical paths or ejecting them entirely from the region. For a planet to maintain a stable orbit near the galactic center, it would need to exist at a safe distance from both the black hole and nearby massive stars. There is also the issue of time variability. The galactic center is not perfectly stable. It experiences flares, energetic outbursts, and changes in gas flow over time. These variations could significantly alter local conditions on relatively short astronomical timescales. Any long-term stability would need to account for these unpredictable changes. Despite these challenges, the possibility of life cannot be entirely ruled out in the outer regions of the central galaxy. Life, as far as we understand it, requires stable energy sources, liquid solvents, and a period of environmental stability long enough for complex structures to develop. While the immediate vicinity of Sagittarius, a star, is far too extreme, regions farther away in the galactic bulge may offer more moderate conditions. It is also important to remember that life in the universe does not necessarily have to resemble life on Earth. Different chemical environments could potentially support entirely different forms of complexity. In theory, life could adapt to radiation levels, gravitational variations, or chemical conditions very different from those on our planet. However, this remains speculative and unconfirmed. One of the most interesting aspects of the galactic center is that it represents both creation and destruction at the same time. Massive stars are born in dense clouds, live short energetic lives, and then explode in supernova events that enrich the surrounding space with heavy elements. These elements are essential for forming planets and, at least on Earth, for supporting life. In this sense, even if the immediate region near the black hole is hostile, it plays a role in the broader cycle that makes life possible elsewhere in the galaxy. The elements that form rocky planets, oceans, and biological molecules are distributed throughout the Milky Way by processes that often originate in extreme environments like the galactic center. So while the central region itself is unlikely to host stable life as we know it, it contributes indirectly to the conditions that allow life to exist in calmer regions, including our own solar system. The galaxy is interconnected in this way, with its most extreme regions influencing its most peaceful ones. The question of life near the galactic center ultimately highlights a broader truth. The universe is not uniform. It contains zones of calm and zones of chaos, regions of stability and regions of extreme change. Life, as far as we can observe, tends to emerge in the quieter spaces in between. And as we continue exploring the hidden heart of the Milky Way, we are reminded that even the most dangerous and extreme environments still play a role in the larger story of cosmic evolution, shaping the ingredients and conditions that make complexity possible elsewhere in the galaxy. The closer we look toward the center of the Milky Way, the more it becomes clear that this region is not only shaped by gravity and orbiting stars, but also by immense bursts of energy that ripple through space. The galactic center is one of the most active high-energy environments in our galaxy, where powerful radiation, shock waves, and stellar explosions constantly reshape the surrounding medium. One of the primary sources of violence in this region comes from massive stars. Unlike smaller stars such as our Sun, massive stars live fast and die young. Their lifespans are short on cosmic timescales, often only a few million years. When they reach the end of their life, they collapse and explode in supernova events, releasing enormous amounts of energy in a very short period of time. A single supernova can briefly outshine an entire galaxy in a crowded environment near the galactic center. These explosions are more frequent than in the outer regions. Each event sends shock waves through the surrounding gas, compressing some regions while scattering others. These shock waves travel for thousands of years, carrying energy and material across vast distances. In addition to supernovae, the central region is filled with high-energy radiation that originates from multiple sources. X-ray emissions are particularly strong near Sagittarius, a star. These emissions come from extremely hot gas that has been compressed and accelerated by gravitational forces. As matter spirals inward toward the central black hole, it heats up to millions of degrees, producing radiation that cannot be seen with the naked eye, but can be detected by space-based observatories. Gamma rays are also observed in the central region. These are among the most energetic forms of electromagnetic radiation, in the universe. Their presence suggests that extremely powerful processes are occurring near the galactic core. Some of these emissions are thought to be linked to past energetic activity from the black hole, while others may be produced by interactions between cosmic rays and dense clouds of gas. Cosmic rays themselves are another important factor in the energetic environment of the galactic center. These are high-energy particles, mostly protons and atomic nuclei, that travel through space at nearly the speed of light. When they collide with gas clouds, they produce secondary radiation and contribute to the overall energy balance of the region. The origin of many cosmic rays is still not fully understood, but the galactic center is believed to be one of their important sources. The combination of radiation, shock waves, and particle flows creates an environment that is constantly changing. Gas clouds are heated, compressed, and sometimes torn apart by these energetic processes. At the same time, these same processes can trigger the formation of new stars by compressing gas to the point where gravity takes over. This cycle of destruction and creation is one of the defining features of the galactic center. It is not a stable or quiet place. Instead, it is a region of continuous transformation, where matter is constantly being reshaped by extreme physical forces. The balance between these forces determines the structure and evolution of the inner galaxy. Despite the intensity of these processes, much of the high-energy radiation does not reach Earth directly in a harmful way. This is because the distance is vast, and interstellar material absorbs and scatters a significant portion of the energy. However, the signals that do reach us provide valuable information about what is happening deep within the galaxy. Space telescopes designed to detect X-rays and gamma rays have revealed complex patterns of emission near the galactic center. These patterns are not random. They trace out structures shaped by magnetic fields, gas flows, and past energetic events. By studying these emissions, astronomers can reconstruct a history of activity that would otherwise remain invisible. One of the most intriguing discoveries in recent decades has been evidence of past energetic outbursts from the central black hole. Although Sagittarius, a star, is relatively quiet today, compared to more active galactic nuclei in other galaxies, there are signs that it may have been much more active in the past. Large-scale structures above and below the galactic plane suggest that powerful jets of energy once erupted from the center. These structures, sometimes called galactic bubbles, extend far above and below the Milky Way. They are filled with high-energy particles and radiation, indicating that enormous amounts of energy were released from the central region in the past. The exact cause and timing of these events are still being studied, but they highlight the fact that the galactic center is not only a place of steady gravity, but also of dramatic episodic activity. When all these factors are combined, the picture that emerges is one of controlled chaos. Gravity holds the system together, while energy constantly flows through it, reshaping its structure over time. Stars explode, gas clouds collide, radiation spreads outward, and new structures form in response. In this environment, nothing remains unchanged for long. Yet beneath all this activity, the central gravitational source remains constant, silently anchoring the entire region. And it is this combination of stability at the core and turbulence around it that defines the true nature of the galactic center. Beyond the bright disk of the Milky Way lies a discovery that changed how astronomers understand the long-term behavior of our galaxy. Extending far above and below the galactic plane are enormous structures filled with high-energy particles and glowing radiation. These structures are known as the Fermi bubbles, and they stretch across tens of thousands of light years in both directions from the center. At first, these bubbles were completely invisible. They do not appear in optical light, and they cannot be seen with ordinary telescopes. Their existence was revealed only when space-based instruments began mapping the sky in gamma-ray wavelengths. In those high-energy observations, astronomers noticed two massive lobes of emission rising symmetrically from the galactic center. The shape of these bubbles is striking. They resemble two enormous spheres or balloons extending above and below the flat disk of the Milky Way. Their edges are relatively sharp compared to the surrounding space, suggesting that they were formed by a powerful and relatively sudden event in the history of the galaxy. The most widely accepted explanation connects their origin to activity near Sagittarius, a star. Although the central black hole is quiet today, compared to active galaxies elsewhere in the universe, it is believed that in the past, it may have undergone periods of intense activity. During these phases, large amounts of matter could have fallen toward the event horizon, releasing enormous energy in the form of radiation and outflows. These outflows are thought to have created powerful jets that pushed high-energy particles outward along the rotational axis of the galaxy. Over time, these jets inflated the large structures now observed as the Fermi bubbles. Even though the original event likely occurred millions of years ago, the bubbles remain visible today because the particles within them continue to emit gamma rays. Inside the bubbles, the environment is very different from the surrounding galaxy. The gas is extremely thin, but the particles are highly energetic. Magnetic fields likely play a role in shaping the structure and maintaining the coherence of the bubbles over such vast distances. Despite their size, the bubbles appear relatively stable, suggesting that the event that created them was not chaotic, but directional and organized. The symmetry of the bubbles above and below the galactic plane is particularly important. It suggests that whatever created them was centered precisely at the galactic core. Random events in the disk would not produce such a balanced structure. Instead, only a central engine, likely the supermassive black hole, could have generated such a large-scale and symmetric feature. The discovery of the Fermi bubbles also changed the perception of Sagittarius, a star. It showed that even a relatively quiet black hole can influence regions far beyond its immediate surroundings. The effects of past activity can persist for millions of years, leaving behind structures that act as fossil records of galactic behavior. In addition to gamma-ray observations, these bubbles are also linked to X-ray and radio emissions. Different wavelengths reveal different layers of the structure, showing how energy is distributed within them. Some regions appear brighter, suggesting variations in particle density or magnetic field strength. The origin of the bubbles is still being studied, and several models exist. Some suggest a single large outburst of energy, while others propose multiple smaller events over time. Regardless of the exact mechanism, all explanations agree on one key point. The central region of the Milky Way has, at times in its history, been far more active than it appears today. The existence of these giant structures also highlights how the galaxy is not a closed or isolated system. Energy from the center can travel far into the halo, influencing regions far beyond the visible disk. In this sense, the Milky Way is connected to a much larger environment through flows of energy and matter that extend well beyond its main structure. From Earth, the Fermi bubbles are invisible to the naked eye, yet they represent one of the most powerful expressions of energy in our galaxy. They remind us that the calm night sky hides a history of violent and energetic processes that shaped the Milky Way over millions of years. As astronomers continue to study these structures, they gain not only information about the past activity of the galactic center, but also insight into how galaxies evolve over time. The bubbles stand as silent monuments to events that once transformed the entire structure of the Milky Way, driven from the very heart of its invisible core. As instruments become more sensitive and observations extend across the full electromagnetic spectrum, the center of the Milky Way continues to reveal signals that do not always fit neatly into simple explanations. Some are well understood as emissions from hot gas, magnetic fields, and stellar activity, while others remain open to interpretation, hinting at processes that are still not fully mapped. The galactic center is one of the most data-rich regions of the sky. Radio telescopes detect complex patterns of emission from ionized gas. Infrared observatories reveal stars hidden behind dust, and X-ray instruments capture flashes of extreme energy from compact regions. When all of these data sets are combined, they form a layered picture of an environment that is both structured and unpredictable. Among the most intriguing features are transient signals, short-lived bursts of radiation that appear and disappear over relatively short timescales. These events can last from minutes to hours, sometimes repeating in irregular patterns. In many cases, they are linked to magnetic interactions near Sagittarius, a star, where strong fields twist and reconnect, releasing sudden amounts of energy. Magnetic reconnection is a process where magnetic field lines break and rejoin in new configurations. When this happens, stored magnetic energy is rapidly converted into heat and particle acceleration. This produces bursts of radiation that can be detected across multiple wavelengths. Near the galactic center, where magnetic fields are strong and dynamic, such events are believed to be relatively common. In addition to these flares, astronomers have observed variations in the brightness of the central radio source over time. Sagittarius, a star, does not emit a constant signal. Instead, it fluctuates, showing periods of relative calm, followed by brief increases in activity. These changes suggest that the environment around the black hole is constantly adjusting as small amounts of matter fall inward or interact with surrounding material. Another category of mystery comes from diffuse emissions that do not always match expected models. Some regions of the galactic center appear brighter or more structured than predicted based on known sources alone. These discrepancies encourage further investigation into how cosmic rays, gas clouds, and magnetic fields interact in such a dense environment. Cosmic rays themselves add another layer of complexity. These high-energy particles travel through the galaxy and occasionally interact with dense regions near the center. When they collide with gas, they produce secondary radiation that can contribute to observed signals. However, tracing the exact origin of these particles is difficult, as they are deflected by magnetic fields during their journey. There are also compact radio sources scattered throughout the central region that challenge simple classification. Some are associated with known stellar objects, while others appear isolated or embedded in dense gas clouds. Each of these sources provides another piece of information about the conditions near the galactic core, but not all of them are fully understood. One of the most important aspects of studying these signals is distinguishing between local effects and large-scale structure. A single burst of radiation might come from a small magnetic event, while a broader pattern of emission could reflect the influence of the central black hole or large-scale gas flows. Careful analysis is required to separate these layers of activity. Despite decades of observation, the galactic center still produces data that invites new questions. Every improvement in resolution reveals additional details, and every new wavelength explored adds another dimension to the picture. Rather than becoming simpler over time, the region often becomes more complex as previously unseen structures come into view. This is not a sign of confusion in the data, but a reflection of the true nature of the environment. The center of the Milky Way is not a static object, but a dynamic system where many physical processes overlap. Gravity, magnetism, radiation, and motion all interact simultaneously, producing signals that carry information about multiple layers of activity at once. In this sense, the mysterious signals from the galactic center are not anomalies to be removed, but natural expressions of a highly active environment. They represent the ongoing interactions between matter and energy in one of the most extreme regions of the galaxy. As observational tools continue to improve, some of these mysteries will likely be resolved into clearer physical explanations. Others may remain partially uncertain for longer periods, not because the universe is unknowable, but because the environment itself is so rich that it produces overlapping signals that are difficult to separate completely. What remains consistent, however, is the central theme. Everything observed in this region ultimately traces back to the same underlying structure, the hidden gravitational core that shapes the motion of stars, the flow of gas, and the behavior of energy throughout the inner galaxy. Even with decades of observation, advanced telescopes, and multiple wavelengths of study, the center of the Milky Way still raises a quiet question. Is everything there fully known? Or could there still be objects hidden within the complexity of the galactic core that we have not yet discovered? At first glance, the region around Sagittarius, a star, seems well mapped. Astronomers have identified the supermassive black hole, tracked the orbits of nearby stars, mapped gas clouds, and detected high-energy radiation across multiple bands. Yet, the environment is so dense and layered that complete certainty is difficult. Each observation is filtered through dust, distance, and overlapping signals. One possibility is the presence of faint or compact stellar remnants that are difficult to detect. Neutron stars and stellar black holes, formed from the deaths of massive stars, could exist in large numbers near the galactic center. These objects do not emit strong visible light, and unless they are actively accreting matter, they can remain nearly invisible. Their presence would only be revealed indirectly through gravitational influence or occasional bursts of radiation. Another consideration involves binary systems, where two compact objects orbit each other closely. In such extreme environments, interactions can produce energetic events, including X-ray emissions or gravitational disturbances. These systems may be present but difficult to isolate from the broader background of activity in the central region. There is also the possibility of intermediate structures that have not yet been fully classified. Dense gas clumps, unusual magnetic configurations, or compact star clusters could exist in regions where observational resolution is still limited. Although modern instruments are highly advanced, the galactic center remains challenging due to its distance and the amount of material between it and Earth. Even Sagittarius, a star itself, continues to be studied in greater detail. While it is widely understood to be the radio emission associated with the supermassive black hole region, the exact structure of its immediate surroundings is still an active area of research. The accretion, flow, magnetic environment, and emission processes are complex and not fully unified into a single simple model. Dark matter, although not directly observable, is also expected to be present in the central region. It forms a halo around the galaxy and contributes to the overall gravitational structure. While it does not interact with light in the same way as ordinary matter, its distribution could subtly influence the motion of stars and gas near the core. However, its exact behavior in such dense environments remains uncertain. One of the most important challenges in studying the galactic center is the separation of overlapping signals. Many different sources emit radiation in similar wavelengths. A single observation may contain contributions from hot gas, stellar flares, cosmic ray interactions, and magnetic activity all at once. Disentangling these components requires careful modeling and long-term data collection. Because of this complexity, it is always possible that some features have been misinterpreted or not yet fully recognized. Subtle structures could be hidden within the noise of stronger signals. Small populations of objects might exist without producing obvious signatures. Even the best data can still contain layers that are difficult to separate completely. However, this uncertainty does not imply that the region is chaotic or unknown in a fundamental sense. On the contrary, the galactic center is one of the most intensely studied regions in astronomy. The limits come not from lack of effort, but from the physical complexity of the environment itself. It is a place where many processes overlap in space and time. Future improvements in observational technology may reveal additional details. Higher resolution imaging, more sensitive detectors, and longer monitoring periods could uncover structures that are currently too faint or too small to detect. Each new generation of instruments tends to reveal that the universe is more detailed than previously thought. Still, even if new objects are discovered, they are likely to fit within the same underlying framework. The dominant structure at the center remains the supermassive black hole, and all surrounding matter responds to its gravitational influence. Any hidden objects would exist within this broader gravitational landscape. In the end, the question is not whether the galactic center is completely empty or fully known. It is whether the layers of complexity have all been fully separated. And given the nature of such an extreme environment, it is likely that the center will always contain subtle details waiting to be uncovered, even as our understanding continues to grow. To understand the true nature of the Milky Way's center, it helps to step back and look at other galaxies in the universe. The Milky Way is not unique. It is one spiral galaxy among billions, each with its own structure, history, and central environment. Yet when astronomers compare galactic centers across the cosmos, a pattern begins to emerge. Most large galaxies appear to contain a supermassive black hole at their core. Some of these black holes are quiet, like the one in our own galaxy, while others are extremely active, consuming large amounts of matter and releasing enormous energy. These active systems are known as active galactic nuclei, and they can outshine the entire galaxy surrounding them. In contrast, Sagittarius, a star, is relatively calm. It still influences everything around it through gravity, but it is not currently producing the kind of intense radiation seen in more active galaxies. This makes the Milky Way center an interesting middle case, neither completely dormant nor violently active. When compared to galaxies with highly active cores, the difference is striking. Some galaxies emit powerful jets of particles that extend far beyond their visible structure. These jets can stretch for thousands of light years, carrying energy and matter into intergalactic space. The energy involved in such processes is far greater than anything currently observed in our own galactic center. However, evidence such as the Fermi bubbles suggests that the Milky Way may not have always been quiet. In the past, Sagittarius, a star, may have experienced periods of increased activity, similar to those seen in other galaxies today. This implies that galactic centers can change over time, moving between active and quiet phases depending on how much matter is available to feed the black hole. Another important comparison involves the size of supermassive black holes. In some galaxies, central black holes are billions of times the mass of the Sun. In others, they are smaller but still massive enough to dominate their surroundings. The Milky Way's central black hole, with a mass of about 4 million suns, sits in a moderate range compared to the largest known examples in the universe. Despite differences in scale and activity, the underlying structure remains similar across galaxies. There is usually a dense central region, a surrounding bulge of stars, rotating spiral or elliptical structures, and an outer halo of older stars and dark matter. This suggests that galaxy formation follows general physical principles that produce similar outcomes under different conditions. One of the most important insights from these comparisons is that supermassive black holes are not isolated phenomena. They appear to be deeply connected to the formation and evolution of galaxies themselves. The growth of a black hole and the growth of its host galaxy seem to be linked through complex feedback processes involving gas, star formation, and energy release. In some galaxies, the black hole appears to regulate star formation by heating surrounding gas or expelling it through energetic outflows. In others, the galaxy provides a steady supply of material that feeds the central object. This relationship creates a long-term balance that shapes the evolution of both structures over billions of years. The Milky Way sits in a relatively stable phase of this cycle. It still contains enough gas to form new stars, but its central black hole is not currently in a high-activity state. This balance allows for a wide range of environments, from calm regions like our solar neighborhood to the extreme conditions near the galactic center. By comparing different galaxies, astronomers gain a deeper understanding of what is typical and what is unusual. The Milky Way center, while complex and active, is not the most extreme example in the universe. Instead, it provides a valuable reference point for studying how supermassive black holes behave when they are not in their most energetic phase. These comparisons also highlight how universal the laws of physics are. Whether observing a quiet galaxy like ours or a distant active quasar, the same principles of gravity, radiation, and motion apply. The differences lie in scale and intensity, not in the fundamental rules governing behavior. Ultimately, the galactic center of the Milky Way is part of a much larger cosmic pattern. It is one example of how galaxies organize themselves, how black holes influence their surroundings, and how matter evolves under the influence of gravity across vast distances. And as we continue to study both nearby and distant galaxies, each new observation adds another piece to the larger picture of how the universe structures itself around these invisible but powerful centers. The supermassive black hole at the center of the Milky Way is not a static object frozen in time. It is part of a long evolving system that changes slowly over millions and billions of years. Even though Sagittarius, a star, appears quiet today compared to more active galactic centers, its future is still shaped by the constant flow of matter, energy, and surrounding stars. At present, Sagittarius, a star, is relatively starved compared to its potential. A supermassive black hole can only grow significantly if it is fed large amounts of gas or disrupted stars. In the current phase of the Milky Way, there is not a continuous large-scale inflow of material into the very center. Most of the surrounding gas is either forming stars, orbiting in stable structures, or remaining too far away to fall directly inward. However, this calm state does not mean permanent inactivity. The environment around the galactic center is dynamic. Gas clouds drift through the central region. Stellar winds push material outward, and occasional objects pass too close to the black hole and are partially captured. These events are rare on human timescales, but meaningful over cosmic timescales. When a star or gas cloud approaches too closely, it can be stretched and disrupted by tidal forces. In some cases, this material forms a temporary accretion disk before gradually spiraling into the black hole. These episodes can briefly increase the brightness and activity of Sagittarius, a star, producing flares and bursts of radiation that are detectable across vast distances. Over extremely long periods, the structure of the Milky Way itself will change in ways that affect the central region. The galaxy is not isolated. It interacts gravitationally with nearby galaxies, especially Andromeda. As these systems slowly move toward each other, their mutual gravitational influence eventually lead to a large-scale merger. During such a merger, the central black holes of both galaxies may eventually interact. This process would dramatically reshape the structure of the combined system. Gas would be compressed, star formation could increase, and the central black holes might eventually merge into a single, more massive object. This future event lies billions of years ahead, but it is part of the long-term evolution of Sagittarius, a star. Even without external interactions, internal processes continue to influence the black hole. Stars in the central cluster slowly evolve, and some will eventually end their lives as compact remnants. Over time, these remnants may drift closer to the center and be captured. This slow accumulation of matter contributes to the gradual growth of the black hole. Despite these processes, supermassive black holes do not grow indefinitely at a rapid rate. Their growth is self-regulated by the energy they release. When material falls inward, it can release enormous amounts of radiation and energetic outflows. These outflows can push away surrounding gas, limiting further accretion. This feedback mechanism helps maintain a balance between growth and environment. In the distant future, the activity level of Sagittarius, A star could change significantly depending on how much material becomes available. It may remain quiet for long periods, or it may enter phases of increased activity if large gas clouds or disrupted stars move inward. Its behavior is shaped not by a single destiny, but by the evolving conditions of the galaxy itself. Even the orbits of nearby stars will continue to change slowly over time. Gravitational interactions, relativistic effects, and long-term perturbations will gradually reshape their paths. Some stars may be ejected from the central region, while others may drift closer. The system is stable in structure, but not frozen in detail. Looking far into the future, the eventual merger with Andromeda will be one of the most significant events affecting Sagittarius, a star. The collision of two galaxies will bring together vast numbers of stars and gas clouds. The central black holes will likely spiral toward each other and merge, forming an even more massive central object that will redefine the structure of the resulting galaxy. In this sense, Sagittarius, a star, is part of a larger cosmic life cycle. It is not an isolated endpoint, but a stage in an ongoing process of galactic evolution. Its current quiet state is only a snapshot in a much longer story that spans billions of years. And as we observe it today, we are seeing the Milky Way's center in a moment of relative calm, a quiet interval between more active phases that may have occurred in the past and may occur again in the future, always shaped by the slow but relentless flow of the universe itself. When all the layers of observation are combined, the center of the Milky Way stops being a single mystery and becomes a structured system made of different components, each playing a specific role in the overall behavior of the region. It is not one object, but many interacting parts held together by a dominant gravitational core. At the very center lies Sagittarius, a star, the compact radio source associated with the supermassive black hole. This region contains the event horizon, a boundary beyond which nothing returns. It is not made of ordinary matter in the way planets or stars are. Instead, it represents a region where mass is so densely concentrated that space and time behave in extreme ways. Surrounding this central object is the innermost accretion environment. Here, gas exists in a highly energized state, often referred to as plasma. At temperatures reaching millions of degrees, electrons are stripped from atoms, leaving behind charged particles that interact strongly with magnetic fields. This plasma does not flow smoothly. It swirls, collides, and compresses as it moves under the influence of gravity. Magnetic fields are an essential part of this structure. They are not directly visible, but they shape the motion of charged particles throughout the central region. These fields are twisted and stretched by rotating gas, creating complex patterns that help channel energy and matter. In some cases, they are responsible for accelerating particles to extremely high energies. Beyond the inner accretion flow lies a broader region filled with gas clouds and dust. These clouds are composed mainly of hydrogen, along with helium and heavier elements created in previous generations of stars. In some areas, these clouds are dense enough to form new stars, while in others, they are being disrupted by radiation and shock waves. The nuclear star cluster surrounds this entire region. It is one of the densest star populations in the galaxy. Within this cluster, stars exist at much closer distances than in the solar neighborhood. The variety of stars here is large, ranging from old, evolved stars to young, massive stars that formed relatively recently. This mixture reflects a long history of repeated star formation events. Among these stars are compact remnants such as white dwarfs, neutron stars, and possibly stellar black holes. These objects are the end states of stellar evolution and are difficult to detect unless they interact with surrounding matter. In the dense environment of the galactic center, their numbers are believed to be significant, even if many remain unseen. Farther out, the gravitational influence of the central black hole becomes weaker and the environment transitions into the broader bulge of the galaxy. This bulge contains older stars distributed in a more spheroidal shape rather than the flat disk structure seen in the spiral arms. It represents an earlier phase of galactic formation, preserved around the central region. Interwoven through all of these layers is dark matter, an invisible component that does not emit or absorb light, but contributes to the overall gravitational structure. While it does not form stars or gas clouds, its presence influences how the galaxy holds together and how material moves within it. Near the center, its exact distribution is still an active area of research. In addition to matter, the center of the galaxy is also defined by energy. Radiation in radio, infrared, X-ray and gamma-ray wavelengths fills the region, each tracing different physical processes. Radio waves often come from charged particles spiraling in magnetic fields. Infrared light reveals hidden stars, and high-energy emissions point to extreme events near the black hole. What emerges from all of this is not a simple object, but a layered structure. Each layer interacts with the others. Gas feeds stars. Stars return material through winds and explosions. Compact objects move through dense environments, and the central black hole anchors everything through gravity. The center of the galaxy is therefore not a single thing that can be described in isolation. It is a system of systems where matter, energy, and gravity are continuously interacting. Its true nature is defined not by a surface or a boundary, but by relationships between components at different scales. And when viewed in this way, the galactic center becomes less like a hidden object waiting to be revealed, and more like a complex engine that has been operating for billions of years, quietly shaping the structure of the Milky Way from the inside out. After traveling through the layers of stars, gas clouds, radiation, magnetic fields, and extreme gravity, the center of the Milky Way begins to take its final shape as a single connected system. It is not a mystery hiding one object, but a deep structure where many physical processes converge into one dominant influence. At the deepest level, everything points towards Sagittarius, a star, the supermassive black hole. It is not visible in the way stars are visible, and it does not shine in any ordinary sense. Instead, its presence is revealed indirectly through motion, temperature, radiation, and time itself. Stars orbit around it with precise paths. Gas spirals toward it in complex flows. Light bends and shifts as it moves through its gravitational field. The event horizon marks the final boundary of this system. It is the point where escape becomes impossible, not because of a physical wall, but because space and time themselves are shaped in such a way that all possible paths lead inward. Beyond this boundary, information does not return to the observable universe, making it the closest thing to a true limit in nature. Surrounding this core is a constantly changing environment of matter and energy. Hot plasma rotates in unstable flows. Magnetic fields twist through space, and radiation is emitted across the spectrum. These processes are not separate from the black hole, but are part of the same system. The black hole does not exist in isolation. It exists through its interaction with everything around it. Farther out, the nuclear star cluster forms a dense, dynamic region where stars live in close proximity. Their orbits trace the gravitational landscape of the center, each one acting like a moving marker that reveals the hidden structure beneath. Some stars will remain in stable orbits for millions of years, while others will gradually shift inward or be scattered outward by gravitational encounters. Beyond this lies the broader bulge of the galaxy, a population of older stars that encircle the central region like a thick halo of history. This structure carries the imprint of the Milky Way's early formation, preserving information about how the galaxy grew and evolved over time. Even farther out, the spiral arms extend into the calmer regions of the disk, where star formation continues at a slower and more stable pace. From these outer regions, the center appears as a bright, obscured core hidden behind dense clouds of dust. yet still influencing the entire galaxy through gravity. When all of these layers are considered together, the center of the Milky Way is revealed not as a single point of mystery, but as a hierarchical system. Each layer depends on the one beneath it, and each one contributes to the overall structure of the galaxy. The black hole anchors the system, the surrounding stars respond to it, and the gas and radiation record its influence. In this sense, what is hidden at the center is not a secret object waiting to be uncovered, but a level of reality where ordinary intuition stops working. Distance, time, light, and motion all behave in ways that require deeper physical understanding to interpret. The true heart of the galaxy is therefore not only Sagittarius, a star itself, but the entire interconnected environment shaped by it. It is a region where matter becomes energy, energy becomes motion, and motion becomes structure on a galactic scale. And as we reach the end of this journey, the center of the Milky Way remains both fully described and still strangely distant, not because it is unknown, but because it exists on a scale where even complete knowledge still feels like looking into something vast, quiet, and endlessly deep at the hidden heart of our galaxy.